Young's modulus by non-uniform bending. Aim of this experiment is to determine the Young's modulus of the wooden scale subjected to non-uniform bending. Young's modulus is a numerical constant, as we all know, that describes the elastic properties of a solid and is named after the 18th century English physician and physicist Thomas Young. Young's modulus is a measure of the ability of a material to withstand changes in length when under longitudinal tension or compression. The Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain, as you all know. Young's modulus is the modulus of elasticity that defines how easily a material deforms or stretches. But why is this number important? Knowledge about the modulus of elasticity of materials will help us to choose the correct material with perfect dimension for a specific application. In engineering, information about the stiffness and elastic limit of an object is essential for choosing building materials and structural materials in general. What is stiffness? Stiffness is the property of a material which is rigid and difficult to bend or deform in response to the applied force. The more flexible an object is, the less stiff it is. Elastic limit refers to the maximum amount of stress or force which a material shows elastic behavior. These are simple basics which we need to know to go further. Now, let us see some examples which will throw light on these parameters. Most of us would have seen a crane used for lifting and moving heavy loads. The crane has a thick metallic rope, you know very well. The maximum load that can be lifted by the rope must be specified. The maximum load should not exceed the elastic limit of a material of the rope. By knowing this elastic limit and the extension per unit length of the material, thickness of the wire can be found which can safely used to lift the load. Also, the Young's modulus of the material is used to know how much weight the bridge can withstand during its construction. So, as you can see, even though Young's modulus developed nearly 300 years ago, it still underpins cutting-edge engineering research that will make tomorrow's buildings, vehicles, sensors, actuators, transducers, and even in medicines possible. In the present experiment, the Young's modulus of the wooden scale subjected to non-uniform bending, as you observe here, is determined by the formula. That is, Young's modulus Y, capital Y, is equal to mgl cube by 4bd cube Y, where capital Y is the Young's modulus of the material of the beam and small y is the depression which we observe using the traveling microscope, having a pin at the center and focusing it while loading and unloading. And m is the mass of the load which we suspend at the center of the beam. G is the acceleration due to gravity. L is the distance between the two knife edges, as you see here, and B is the breadth of the scale, which we have to determine using the vernier caliper. Having the vernier caliper, try to know the breadth of the scale, and the thickness of the scale we have to determine using this is the thickness of the scale which we have to find using the screw gauge. Is it clear? To measure the Young's modulus, the apparatus required are, as I have mentioned already, the wooden scale as you see here, and slotted weights what you have here, and a traveling microscope to observe the depression by focusing it to a pin which is kept at the center of the beam to know the depression. And the screw gauge, as I told you, to measure the thickness, and vernier caliper to measure the breadth of the scale.
This is the beam for which the depression should be calculated when it is being loaded in a non-uniform way. So when I say it is a non-uniform, you know we will be having a pin here, it will be loaded at only one end. To place the beam, I will be having two knife edges. I will be placing the beam with 20 centimeter apart towards my left and the right. So when for a 1 meter scale, if we reduce the 20 centimeters towards the left and the right, in between the knife edges we will be having 60 centimeter, which is the length of the beam. To measure the depression, we will be having a mark whose reference mark will help us to note down the depression happening due to the loading. I will be placing the beam, and these are the slotted weights which has been given to us. There will be in terms of 50 grams each, will be given with 250 grams. So initially I will be loading this beam with a dead weight called W. Before measuring the actual reading, we have to set this beam to an elastic mode such that the loading and unloading values remains the same, for which I will be using this slotted weights W, and I will be loading with 50 grams, that is W plus 50. Before taking the reading, we have to set the beam in this fashion of loading and unloading. As you could see here in this image, there is a dead weight hanged here. This will be taken as a point of reference whose value can be noted through this traveling microscope. When I add a 50 grams to it, the beam will get depressed due to the extra load, which is impossible to see through the naked eye, but it can be measured through this apparatus called traveling microscope. The method of taking reading in the traveling microscope is exactly similar to that of an vernier calipers. The only difference is in the least count value. As it has been mentioned, the value of one main scale division in the traveling microscope is 0.05 centimeter. The total number of vernier scale division here is 50. So the formula for least count is one main scale division, that is 0.05 whole divided by total number of vernier scale division, which is 50. That gives me a least count value of 0.001 centimeter. For calculating the depression of the cantilever using non-uniform bending method, our prime focus is to focus the pin, for which I will be bringing this microscope very close to the pin. If it is been positioned in the downward direction, you have to adjust and you have to take them very close to the tip of the pin and fix this screw. To focus the tip of the pin, we will be adjusting this microscope. Entire setup is been moved towards back side, and from which I will be adjusting the eyepiece using this screw. Inside the eyepiece, we will be seeing a cross wire, a plus mark cross wire. The tip of the pin will be looking inverted. It will be inverted. So the tip of the pin will be focused towards the horizontal cross wire. This is for loading, that is for W by hand. Now then I will be first taking the reading of what is the main scale. and what is the vernier scale coincidence. And we will be recording in the loading part of W. Now let us see how to take the reading in the vertical scale of the traveling microscope. Here, as you could see here, the 0 of the vernier is exactly in between 8.75 and 8.8 of the main scale reading. So in that case, since it has crossed the minimum point of 8.75, the main scale reading for this particular portion is 8.75, and the vernier scale coincidence is noted by seeing the exact division of coincidence with that of main scale. Vernier scale has totally 50 divisions, in which in our case the 23rd division is exactly coinciding with that of the main scale reading. So that is, the 23rd division of the vernier scale is called the vernier scale coincidence. And once the values are noted, now we will be taking another 50 grams and we will be loading them here. What will happen? Due to the extra load or force, there will be a small depression happening in the cantilever, which will alter the alignment of the pin towards the horizontal cross wire. Now the pin would have been moved a very small distance apart from the horizontal cross wire. The prime aim to note down the depression is that can be done through this fine adjustment screw. Now I will be seeing this through microscope, through the eyepiece, and I am making the fine adjustment screw such that the horizontal cross wire moves close towards the tip of the pin. So by rotating this fine adjustment screw, what we have done is we have changed the position of the vertical scale, which will show another reading due to this load. Now we can note down the main scale reading and vernier scale coincidence for the load called 50, that is W plus 50 grams. While making the fine adjustment screw rotation, if it is being moved in a clockwise direction, we have to keep on moving in a clockwise direction. We should not come back into an anti-clockwise direction, then we should not move towards a clockwise direction. This is called as a backlash error, which will add error towards our values which we are calculating. Likewise, when I add 50 grams with W plus 50, it will become W plus 100. So as you could see here, due to the extra loading of 50 grams in the slotted weights, the beam will undergo a depression such that the alignment of the pin towards the horizontal cross wire would have moved up, which I can able to see it through my eyepiece with the microscope attached with this. This eyepiece will enable me to show how far the tip has been moved up. Once the tip has been moved up, I will be using this fine adjustment screw and adjust that such that the horizontal cross wire touches the tip of the pin. Now, since the scale has moved up to make the marking in the tip of the pin, the difference in the reading can be noted down here. This is for W plus 100. Likewise, I will be adding W plus 50 grams, which is nothing but W plus 150. Again, the movement or difference in the reading can be noted down here. I will be adding another 50 grams, which is W plus 200. Note down the difference in the reading by moving microscope, and this is 50 grams again, which is W plus 250. Once W plus 250 grams is been added, you have to note down the reading for it again. This completes the loading part. As you could see here in the table, we have to do the same procedure for unloading. So the W plus 250 reading towards the left of your tabular column, which is at the bottom of the loading, the reading is exactly will be the same towards the bottom of the reading in the unloading part. So write down the same value of W plus 250 of loading and unloading to be the same. So once W plus 250 reading is been noted, I will be removing the 50 grams. Now it is 200. When I see this here through this microscope, the tip of the pin would have been moved from the horizontal crosswire. Again, by adjusting it, I can able to note down the exact movement of the scale, which can be recorded in your observation. Likewise, I will be removing another 50 grams, note down the values. Likewise, you have to move every 50 grams stepwise, note down the difference in the values. This completes the reading of loading and unloading for non-uniform bending. Now let us see how to calculate the load and the depression using this tabular column. As we have seen already, when the dead weight W is hanged in the beam, which is a non-uniform bending in our case, the value of W from the vertical scale reading, we will be noting the main scale reading and vernier coincidence, from which the total reading can be calculated. For calculating the total reading, we have to multiply this vernier scale coincidence with the least count of this traveling microscope, which is 0.001 centimeter. So when the vernier scale coincidence value is multiplied with the least count, it becomes vernier scale reading. Once the total reading for W has been calculated, we will load the dead weight again with 50 grams, that becomes W plus 50. Likewise, we have to note down the main scale reading, vernier scale coincidence, and calculate the total reading. Similarly, we will be adding weight in terms of 50 grams until we reach a point called W plus 250. Once this value is recorded, this completes our loading part. Once the loading part is completed, the W plus 250 reading is exactly repeated here. We are going to write the same value of W plus 250 for loading, and this value is written here for unloading as well. And now we have to remove the 50 grams and note down the main scale reading. Likewise, note down the vernier scale coincidence. And again remove the 50 grams, it will become W plus 150. Likewise, removing every 50 grams, we have to reach a point at an initial stage where the W is being loaded. Now let us see how to calculate the mean value for the loading and unloading. The mean value for W is noted by taking the total reading for loading for W, likewise the total reading for unloading for the dead weight W. Taking the average of these two will give us the mean value. Likewise, we have to calculate for W plus 50, taking the total reading of loading, taking the total reading of unloading, find an average of it and substitute. Likewise, we are supposed to calculate all the values till W plus 250. Once the mean value is calculated, we will come to this column called depression, for which the depression is calculated for 50 grams. Since it is for 50 grams, we will be taking the mean value of W and we will find the difference with respect to W plus 50. So the difference of these two values will give us a value. Likewise, W plus 50 and W plus 100. The difference is 50 grams. Likewise, W plus 100 and W plus 150. The difference is 50 grams. So take the difference of these two mean values and we will get the depression for every 50 grams. Here it is worth noting that you will be having 6 values in mean, and since we take a difference, you will be getting the 5 values over here. Now let us see how to calculate the last column called M by Y. M is the mass for which we have calculated the depression called Y. So we will be substituting M in 50 grams over Y. This is the value. Likewise, M by Y can be calculated for all the 5 values. At the end, we will be taking the mean value for all these 5 values. That will be the M by Y value for this particular table. Now let us take the vernier close to the breadth of the scale and move the sliding screw such that the fixed end of the jaw gets hold of the scale. Once it is been fixed, we will tighten the screw such that the lower jaws will not move further, so that we can take the readings carefully. In this case, the main scale reading here has crossed 26th division. How do we tell that? Let us see in detail. The main scale reading is taken as the point where the zero of the vernier indicates the division in the main scale. In this case, the zero of the vernier has crossed 26th division of the main scale. Hence, we note the main scale reading as 26. And we have to carefully look into the instrument straightly such that one division in the vernier will be exactly matching with the main scale reading. In this case, if the 5th division in the vernier is coinciding with the main scale, here we need to write this, the vernier scale coincidence division, as 25. Now let us see how to record the values of vernier calipers for the breadth of the scale in the tabular column. Zero of the vernier coincides at 26th division of the main scale, and between 0 to 50 divisions in the vernier scale, we said it is the 5th division, that's 5, number 5 in the vernier coincides exactly with the main scale, which is nothing but the 25th division of vernier. How do we convert this coincidence into reading? Formula says the vernier scale coincidence into the least count. When we multiply it, it is 0.50. 25 into 0.02. Now the original reading can be written as from the value of main scale reading plus vernier scale reading, which is nothing but 26 plus 0.50, which is equal to 26.50. The last column is the correct reading, which we correct from that of an original reading. if we have any errors. In our case, the zero error is nil or it is zero, hence the correct reading is exactly the same as that of original reading, which is 26.50. Now let us see how to determine the thickness of the given beam. Rotate this until the scale is being holded by the screw gauge clearly. So now we'll ensure the spindle and the anvil holds the scale, and to ensure its stability, we'll rotate the ratchet, and if it gives one small indication with the sound, we confirm the spindle have holded the scale clearly. Now let us look into the reading. Above is the marking called 5 millimeter, and below is 5.5, and again above the point will be 6. Now the pitch scale reading in this measurement is 6 millimeter. Now let us say what is head scale coincidence. Coincidence is nothing but the division in the head scale. Now we can see here is 5, here is 10. So it has crossed 9, and hence the head scale coincidence, the line joining from the pitch scale where it indicates the division in the head scale, is what is called as an head scale coincidence. Coincidence is, we'll be writing in terms of divisions. So simply write this as 9th division. Now let us see how we can able to enter the values of screw gauge which we have measured for taking the thickness of the beam, that is the scale. This is the PSR, the pitch scale reading. The reading that we note from the pitch scale of the screw gauge, we are supposed to record here. We have recorded that value as, we measured that value as 6. Head scale coincidence, that is the line joining the pitch scale where it ends up indicates the value on the top of an head scale. That's what we call it as a head scale coincidence. Since it is a number, that's a division, the unit is division. The value that we have measured from the scale is 9. We are entering. HSR represents the head scale reading, which is nothing but a product of multiplying the least count with that of an head scale division, that is 9. We will multiply 9 into 0.01, which you don't have to mention here. You can directly write the value as 0.09. OR represents the original reading which we have obtained from the toughen measurement. It tells you the PSR plus HSR, which is nothing but 6.09. This is the original reading. Coming to the last column, which is the correct reading, which has to be corrected with that of the zero error of an instrument. Every instrument has its own zero error. As we have previously seen, what are the 3 cases of measuring the zero error? Again, I am bound to remind you that we have to note down the zero error before taking the reading. In our case, we take the zero error is 0. So in this case, there will not be any change in the original reading. So 6.09 is the final reading of thickness of the beam. Likewise, we are supposed to take 2, 3, 4, 5 different set of readings. All those 5 different set of readings for a 1 meter scale, we will be keeping at 5 different positions and we will record that. Now let us see how to calculate the Young's modulus of the beam using non-uniform bending, for which the formula is given here. Here we know G is acceleration due to gravity 9.8. L is the length of the beam between the knife edges, which is 60 centimeters since it is 10 to the power minus 2 meters, and B is the breadth of the beam, which is 26.5 millimeter into 10 to the power minus 3, and D is the thickness of the beam, which is 6.09 millimeters, which is represented as 10 to the power minus 3. The M by Y value is shown here, which is nothing but the average value of the 5 readings which we have taken from the tabular column to calculate the depression of the beam. And that average value is represented here. Don't forget to mention the 10 to the power plus 2 value in this case. So what we have done is, in the calculation part, we have taken the exponential terms separately, as the cube is minus 6, the 2 stands here as such. Similarly, 10 to the power 3 stands here as such. The product of minus 3 into 3 becomes minus 9. So rest of the calculation is simple. Multiply the numerator and write the value here. Multiply the denominator and write the value here. And you can cancel out these values by yourself, from which the final value of the Young's modulus of the beam by non-uniform bending is this one. Now let us see how to calculate the Young's modulus using graphical method. This part we will be explaining how to verify the Young's modulus through graph. The tabular column reads as such: the load at the hanger M, the weight W 100, 150, 200, 250. The depression for the load is being calculated with respect to the dead weight W. The value of 0.036 has been obtained by making the difference between the W and 50 of the mean value. In the previous tabular column, from the mean value, you take the W and W plus 50, and the difference is mentioned here. Likewise, from the W of the mean value and W plus 100 of the mean value, the difference is mentioned here. Likewise, we will be calculating the difference for 50, 100, 150, 200 and 250. Let us see how to plot the graph between the depression and the mass that is suspended in the beam. This graph is plotted from the values taken from this table. As you could see here, initially mark all the points. The load is taken along the x-axis and the depression is taken along the y-axis. Corresponding to 50 load, mark the point all along the y-axis. Similarly, first initially mark all the points, and now once all the points has been marked, let us find what is the maximum probable points that it will be linear towards a line, for which we will be keeping the scale aside and we will be checking what is the maximum point which will be covering under the straight line. So in this case, we are getting 3 points passing to a straight line. Let us draw a slope connecting these 2 points, and this is the point. This is called dy, and this value, the difference is dx. As we know, slope is dy by dx. Calculate the difference between these 2 points, represent it as dy. The difference between these 2 points along the x-axis is dx. The ratio of these two values will give us the slope. The formula to calculate the Young's modulus using graphical method, the only difference here you can find is it is 1 by slope value, which is nothing but here we will be getting the values as y by m. Since our formula is m by y, we have represented as 1 by slope. In our case, calculate the slope value. In the formula, substitute the value here. Substitute the slope value directly here. You will get the exact value of Young's modulus. This graphical method of calculating the Young's modulus should be verified with the practical measurements which you have done with the formula. This graphical method of an Young's modulus, the previously calculated Young's modulus should be recorded in the result as well.
Where do we have such applications? Where do we use Young's modulus or elastic properties of a material? This is where we apply Young's modulus on both very large scale systems such as turbines, in jet engines, and in small scale microelectronic mechanical systems where we make objects from 1 to 100 micrometer of pressure sensor, actuators, motors even within a dimension of 1 to 100 micrometer, which we refer it as a MEMS. In such MEMS, microelectromechanical systems, we have microcantilevers which are used as sensors, actuators, transducers in medical, electrical and electronic industries, and microcapsules used in even in pharmaceuticals. So moreover, in a very large scale applications, short cantilevers used in balconies. When you construct a home, there may be a balcony, and where you have a cantilever structure, and longer cantilevers that are used for diving boards. In the swimming pools, when you go, you can see the diving boards. So next, coming to the MEMS again, a longer flexible micro cantilever, 100 microns, works as a best transducer or sensor. What is a transducer? A device which converts one form of energy to another. A sensor is like a thermocouple which converts heat energy into a voltage. A thermocouple is a sensor. Flexible micro cantilevers are used in atomic force microscopes, diagnostic transducers, chemical sensor arrays where an external force or intrinsic stress causes the cantilever to flex or bend. So these are the areas where we use the flexible micro cantilevers. More rigid cantilevers also we use where the size is of the order of 10 microns. They are used as needles, probes or transport mechanisms for probes or transducers. In general, microcantilevers are commonly employed in atomic force microscope, read-write storage devices, environmental monitoring and RF switches which we use in communication. So in electrical, electronics, mechanical, civil, in all areas we use elastic properties, in particular Young's modulus or stiffness, this property in most of the applications. Some of the interesting questions with reference to the modulus of elasticity of a material. 1. How does the width of the cantilever affect its flexibility? Question number 1, please think about it. Can you mention the 5 factors that affect the Young's modulus of a beam? Yes, you should know about it by this time. How to realize the same stiffness in 2 beams with the different lengths? Yes, you have to think little more.